look at some log expressions and figure out what they equal. So here are some questions for you. Suppose we ask for the ln of 1. Okay, that's really saying what power do we put on e to get 1? And the answer to that would be 0, because e to the 0 is 1. How about this question? Ln of e to the 0. So you could do this two ways. You could say, well, e to the 0 is 1, and it's the same as the first question. Or you can say, this is asking a very silly question. It's saying, what power do I put on e to get e to the 0? Which is 0, by definition, the way it's being asked. If you think about it the second way, then this question's very easy to do. This is saying, ln of e to the 5th really means what power do we put on e to get e to the 5th? That has to be 5. Okay? And then there's a few more fun little questions. Okay, how about this? The ln of the square root of e. Well, it doesn't quite look like the previous two examples until you realize that you can rewrite it, right? Square root of e is really e to the 1/2. That's saying what power do you put on e to get e to the 1/2? 1/2 is the answer there. Okay, here's another one that's the same fashion. Ln of 1 over the rad of e is really the ln of e to the negative 1/2 power. And that's 1/2. Oh, sorry, negative 1/2. Let's look at the one more interesting question. Suppose you had e to the ln of 2. All right? So I guess a way to think of this is, like, sort of just take a minute and ask yourself what that exponent means. Here's a way to do it. This ln2 means it's equal to, or I should say, it's the power we put on e to get 2. That's what ln of 2 is asking. Now, chances are you don't know what that number is. But it doesn't matter. I'm putting that number on e. So by definition, I have to get 2. Okay? So e to the ln of 2 is just 2. In general, we can say if you had e to the ln of something like triangle, you get this triangle. Just be careful. You need to restrict triangle to numbers that are greater than 0. You can't take the ln of 0. You can't take the ln of a negative number. All right? The earlier examples, the other ones up here, here, and here, for example, all these guys in particular, demonstrate a different rule. The rule is that if you have the ln of e to the triangle, you get back this triangle. And in this case, there is no restriction for triangle because you could do e to any power you want. You could do e to negative powers, and it still makes sense. You don't get anything undefined. Right again. So let's consider a few more. Suppose I tell you this, that x is equal to the log of a, and y is equal to the log of b. All right, and then we're supposed to rewrite some expressions in terms of x and y. Now, one quick comment. When you see this, what you should do is quickly change it into the exponential form, right? Every log statement has an exponential form equivalent. Remember that these little logs have base 10s on them. So another way to write this first statement is to say 10 to the x equals a. And for the second statement, we have 10 to the y equals b. And now we're ready. We can go through all the questions that were being asked. So suppose I said, how would you rewrite the log of a times b in terms of x and y? Well, that's just log a plus the log of b by the first rule log we have. Then we just sub in. We get x plus y. I'm going to make one up for a minute. Suppose you had the log of a plus b instead. I'm going to say a lot of people are going to want to use Rule 1 on there, right? Rule 1 only works for when you have the product of a times b and you're taking the log of that. In this case, we really can't do much other than sub in what a and b are. So we can say the log of 10 to the x plus 10 to the y. And we've achieved our goal, because our goal is to write this in terms of x and y. Okay? Some people might try and distribute the logs onto there. That does not work. That's not one of our rules. Okay? Let's try a different example. Suppose you had this question, just a times b. Okay? Well, you know that a equals 10 to the x, because we wrote that up here, and then b equals 10 to the y. So you have 10 to the x times 10 to the y, or 10 to the x plus y. Okay, so let's try another problem. Suppose you are given the following facts. P equals the ln of m, and Q equals the ln of n, and we ask about these expressions. What's another way to write the ln of n times n to the fourth? Okay, and we're supposed to write our answer in terms of P and Q. Well, here we can see we have a product of variables, and then we have one variable to the power of 4. So I'm going to rewrite it this way. And I can do that by the first rule. It says that the ln of a product, or the log of a product, is the sum of the two logs, right? Okay. Now, I'm tempted to do some stuff here, but the only problem is this. ln n is equal to q, so I'm happy about that. But this doesn't quite match this. We know that the ln of m by itself is p, but the ln of m to the fourth is not p. So what other rule can we use? We know if we have an exponent, we can put it in front. So we get the ln of n plus 4 times the ln of m. Okay. And now we're all right because of that was the third rule, right? The rule that says the ln of a to the c power is c times the ln of a. That's what we just used here. And we can actually sub in what we know. So for example, ln of n is equal to q, and the ln of m is equal to p. So that's it. We've achieved our answer because our answer is written in terms of p and q. All right? Let's look at another one. So the next question was the ln of 1 over n. Okay. That's not quite the ln of n that we have up here. It's 1 over n, but I can rewrite it. I can write this as the ln of n to the negative 1 power, right? And then by the third rule, I get negative 1 times the ln of n. Well, that's just negative q. That's that expression. Okay, here's a question where you're tempted to go use one of your rules of logs, but you shouldn't. ln of m, over the ln of n. It's very tempting to think, oh, that's rule 2, right? But rule 2, if you recall, looks like this. The ln of a over b equals the ln of a minus the ln of b. And that's not what we have here. These two things do not match. So it's tempting to make this ln of m minus ln of n, but that would be incorrect. You can't apply any of the rules that we have. What can you do? You can go up and just remember, oh, ln of m is p and ln of n is q. So this is just p over q. It's actually a pretty easy question. All right? All right. So let's look at a few equations. How can we use these rules of logs to help us out there? So here's one. 5 times 1.031 to the x is equal to 8. Okay. This is the kind of equation that logs or ln's can really help you with. Okay, and I'm saying that because you know when you have a variable in the exponent, it's a little bit different than other equations you've seen in the past. Well, I'd like to get that variable out of the exponent. That's my goal. And I only know one rule that can help me. And that rule that can help me looks like this. The log of a to the c power is c times the log of a. I haven't made a big deal about this yet. I should now, and I should tell you that this rule is just super important. It's the whole reason we can solve exponential equations, right? Because it gets exponents and makes them coefficients. So I'd like to use that rule if possible. So I'm thinking I want to take the log of both sides. The only problem is this 5 here does not have an exponent on it. So instead, what I'm going to do is I'm going to divide by 5 first. Get that 5 to the other side. I'll get 1.031 to the x power is 8 divided by 5, which is 1.6, I guess. Okay? And now, if I look at the expression on the left, it's a number to an exponent. And I don't want that exponent to be there anymore. I'm going to get it in front, so I'm going to take the log of both sides. The log of 1.031 to the x equals the log of 1.6. And I could bring the x in front. And now I'm done. x equals the log of 1.6 over the log of 1.031. Okay? Interestingly enough, we talked about change of base formula. We could also write this as the log base 1.031 of 1.6. Sort of fun to do if you want. Okay, change of base formulas are everywhere, aren't they? Okay. So let's look at another equation. So here you have 3 times 2 to the x plus 8 equals 25. Well, just like always, you like to get x alone. So we'll start by getting 2 to the x alone, and then we're going to use our log rule again. So minus 8, so 3 times 2 to the x, and then 25 minus 8, 17. Divide by 3, and you get 2 to the x equals 17 thirds. And now I'm in a desirable location because the thing on the left just has a number to an exponent. I'd like to have that exponent come down in front, so I'll take the log of both sides. So I get the log of 2 to the x equals the log of 17 thirds. Put the x in front, x log 2 equals the log of 17 thirds. And then last, I can divide by log 2. So I get x equals the log of 17 thirds over the log of 2. Now, I'm just going to take a minute and comment about this answer, because this answer can be written quite a few different ways. So, for example, somebody might decide, hey, I'm going to use rule 2 on the top and get the log of 17 minus the log of 3 over the log of 2. Right? That's not log base 2, sorry. That was a little small there. Over the log of 2. Okay? But that's not the only thing you could do. If you are dividing a difference by another number, you can divide that number into both parts. So you could make this the log of 17 over the log of 2 minus the log of 3 over the log of 2. Then you could still have more fun. You could use the change of base formula. You could write this as the log base 2 of 17 minus the log base 2 of 3. Okay? But then you can use rule 2 again and say, hey, this is the log base 2 of 17 thirds. So there's quite a few ways to write the same answer.